Okay, we're getting started. In terms of announcements, your homework 2 is up and available for you to get started on. After today, I think you should be able to do all of it. So make sure you get started. But you definitely can do the C problem. The C problem has to be written in C. You can't do it in C++. So be aware of that. Your Chapter 2 quiz should be available over the weekend. It's really short, pretty simple, right? Chapter was short and simple, so don't expect it to be as long as Chapter 1. And then, like, the next Chapter 3, the next quiz isn't really Chapter 3, but, like, the assembly quiz probably will come out, like, the following week for you to work on. And the midterm fairly soon as well. Any questions before we get started? Okay, so, right, we were translating common C expressions over to assembly code. We were working with the advanced indexing mode. When you use it, again, it looks like DOIS, and the effect of this expression is to get the memory at location D plus O plus I times S. Or again, it looks like dereferenced D plus O plus I times S, that location of memory. The displacement, the D field, has to be a constant expression. The offset has to be a register. Index has to be a register, and scale can be 1, 2, 4, and maybe 8. If you don't give the displacement, offset, or index, they will default to 0 if you don't provide them. If you don't give the scale, it defaults to 1. The scale is really affected by the size of the instructions you're working with. So if you are working with characters, what would your scale be? 1. If you were working with shorts, your scale would be 2. And if you're working with integers, 4. If you're working with floats, how many bytes big is a float? 4. So you would use 4, right? If you were working with an integer pointer, 4. Because a pointer is going to be 4 bytes big. It stores an address. And on a 32-bit machine, there's 32 bits for an address, so 4 bytes. If you were working with a character pointer, 4. If you're working with a short pointer, if you're working with a double pointer, 4. If you're working with an integer pointer, 4. Right? All pointers are the same size, is what I'm trying to get at there. So pay attention to that. And now we're just going to go ahead and work on translating some common things, common like array type expressions that you're going to see. And we'll do one version with AR being a label in the data section, and the other with AR being a register. Remember, the labels in the data section, they are constants. They just refer to some constant location in memory. We don't know exactly what that number is going to be, and we don't really care, to be honest, but it's going to be some fixed location in memory, right? So that's why the labels can show up in the D field. So let's copy this. Let's say we wanted to do AR at 7. And again, what do you want array to be? Do you still want it to be an array of ints? I mean, you know, it's probably good to see some examples where it's different things just to see how it's different. It won't be much of a change, but let's say it's an array of shorts. And then again, it's an array of shorts. So again, our expression AR at 7 is still going to be translated to star AR plus 7. Now, in this expression, what parts are constant in AR plus 7 on the left-hand side, assuming that AR is label? So is AR going to be constant? Yeah, it is, because it's a label, right? What about 7? Is it constant? Yes. So since these are both constants, where do they have to appear in? They have to all be in the displacement field, right? So here we're going to move L55 to where? Again, there's no ECX here in this problem because we don't have a constant. So what are we going to put in the AR field? I mean, on the AR field, in a displacement field, the D field. Because again, you said AR is constant and 7 is constant, right? So they both have to go into the displacement field. You can put a constant expression there. So what do you want your expression to be? Discuss amongst your neighbor what you think should go into the displacement field. What your constant expression should be. So any thoughts what we should put into our displacement field? Yeah, why not? You're very close, but slightly wrong. It's not what you put is wrong, it's that you forgot to put something. Not a dollar sign, because if we do the dollar sign, it's going to be treating this expression as a constant. And can you move a constant 55 to like the constant 107? No, right? We want to move it into memory. Yeah, AR plus 7 times 2. The times 2 on the 7. Because we have an array of shorts, and we want to move 7 shorts, and each short is 2 bytes big. So we need to move 7. The other thing is this is not going to be a move L anymore, but a move W, because we want to move a 2-byte quantity into memory, not a 4-byte quantity. Does that make sense? So let's say down here on this next line, I wanted to do something like EAX is equal to AR at 2. How would you translate that? Shouldn't say EAX, it should be AX, because it's a 2-byte quantity. What would that look like? So we need to do a move. What should our suffix be? W, right? Because we're trying to get a word size quantity. Where from memory do we want to start reading? Where in memory do we want to start reading from? AR, right, plus 3 times 2. Right, and, just to make sure that we know where the times 2 is going. So, it's around there. And we would like to put that value into AX. How is this line different from this line? What's the effect of this line here in C code? Yeah.
So we will get the first element of AR and then plus it with 6 and then put that value into EAX.
So you're saying that this line of code is equivalent to doing star or like EAX is equal to star AR plus 6?
Yeah.
Do you guys agree? Any other alternatives? What you think this might be? Because it's not this. Yeah. Well, in terms of C code, right? You wouldn't plus 6 because it'd be like plus 2 because you want to move 2 shorts. But it's either equivalent to AR plus 2 or AR plus 3, my bad. AR plus 3, or if you want to look at it, it's the address of AR at 3. Like, because $sign means constant, right? And the constant part of a label is where it's at in memory. So this part over here is essentially doing AR plus 3 in C code, because the compiler will take care of the size of the variables for you, so no times 2. So just have to be careful with what you're doing and make sure you get the right thing. If you're not seeing $signs, it means you're accessing something in memory, right? If you're seeing $signs, you're working with a constant, right? And again, the constant part of a label is where it's located at in memory, the address. So the constant part of a label is where it's located at, right? Which would be its address, right? Because again, you know that labels have to be constant, right? Because we're using the label over here. Oops. We're using the label over here in the displacement field, right? This is nonsense, right? Move a constant into a constant. Like move 5 into 7. 5 equals 7. That doesn't make any sense, right? But this says go to that location in memory and get the value that's there, right? But it's some constant location. It's still able to appear in the displacement field. So it'll go to that location in memory and put the value there. If we go over here to the right-hand side, is AR constant or not? Given that AR is in EAX. Yeah, it's not constant because it's in a register. Registers can't be constant. They're registers. 7, of course, is still constant, so what's our expression going to look like over here? So you want 7 parentheses. You want to do AR? So comma, comma. So comma, then AR. Okay, so there are some problems here. The first is that AR, it's a label, right? But you can only put registers in the offset and index fields. So we can't have AR showing up here. Also, AR is in EAX. So if you wanted to, you could do %EAX, because that's a register that has the same value as AR. And that would be fine. But there's one other mistake here. Right? We need the 2 times the 7. Right? Because again, we're still moving shorts. And this move L still needs to become a move W. And this yeah, that's still EAX, but move W. And here, we can close this up and that'll be fine. And you can either have the comma here or not, because but I personally wouldn't put the comma there, so I wouldn't have to write it. Because it's just going to add EAX, the array. Right? So this is still AR, right? Plus 2 times 7. AR plus 2 times 7. Or, 7 times 2, however you want to look at it. Any questions before we go to the next example? Yeah. Because it's an array of shorts, and shorts are 2 bytes big, and the W suffix means 2 bytes. All right, the L suffix is how many bytes? The L suffix is how many bytes? 4 bytes, right? And we don't want to move 4 bytes because that would be moving 2 shorts instead of 1. Anything else? Yeah.
So you do 7 times 2, that moves it over 7 times 2 times. But what's the difference between putting 2 in the left, like after in the
So like inside here, like doing comma 2 here,
yeah, in the last, what's it called?
the scale field.
The scale field.
Again, you have to look at the advanced indexing mode and look at the expression that evaluates. It's D plus O plus I times S. Right? Notice the scale field is always multiplied by what's in the I spot. Oops. The I spot right here.
Okay.
Right? So if we want to multiply I by 2, then we'd have to have something in I, and then the 2 would go in the scale field. Now let's say we combine the two things that we had last time, and let's say we want to do AR at I plus 3 is equal to 55. What do you want AR to be? An array of what? Sure, it's an array of characters. Right, so AR at I plus 3, again, it's translated to AR plus I plus 3. AR, is it constant? Yes, because again, on the left-hand side, it's still a label in memory. As long as it's a label in memory, it's always going to be constant. It will not change, right? Because you might change what the value at that location is, but again, AR is referencing the location. The location does not change. So the labels will always be constants. So 3 is, of course, a constant. And we will say, again, that I is in ECX. So is I constant? Not constant, right? So when we go to write our expression now, it's going to be move what? Given that we're working with characters. Characters are how many bytes big? 1, so it's going to be move B, right? We're still moving the value 55. Again, what parts of this expression are constant? Well, the AR is constant and the 3 is constant. So AR, right, is constant. AR plus 3, that's a constant expression. What do I need to multiply the 3 by? 1, right? I'm just putting it there so that you know it's kind of consistent pattern, but you could just write 3, of course, because 3 times 1 is 3. So now over here, what should we put in our parentheses? Do we want to use the offset field? Or do we want to use the index field? Again, this is the expression that we're working to get. Right, these are two big things. So do we want to use the I field or do we want to use the O field? O. I. The rest of you want to use S? It was the only option, right? If you didn't vote for the first two. So again, think about what this expression is going to compute. We already have the D, which is the AR plus 3, right? Do you want to use the O field or do you want to use the I field? O, I. Man, a lot of you guys are still wrong. You still keep picking the scale field. You got to pick something, right? For those of you that are picking the offset field, why do you want to pick the offset field to put I in? Right, ECX in. Right, because we know that if we ECX is I, it's a register, right? Which means it has to go in the offset or the index because the scale can only have 1, 2, 4, or 8. And ECX is not 1, 2, 4, or 8, so it can't be scale. Right? Because ECX is just some arbitrary number. It's in a register too. You can't put registers in the scale. Right? So over here, we have offset and index, right? If we put it in offset, is just going to be what the value in the register is. If we put it in the index, it's going to be multiplied by the scale, right? What should we be using for our scale for this problem? 1, right? So if we put it in the O, we're just going to get ourselves ECX. And if we put it in I, well, it's going to be ECX times 1. So it doesn't really matter which one we pick. Because why? Does not matter for this problem right now. Because it's 1, right? Because we're working with characters. If we're working with anything besides characters, where would we want to put it at? The I field, right? So we should probably just be consistent and always use the I field, right? To make sure it's lining up in the right spot. Right? So I will put it still in the I field. So %ECX. And then again, you can put the 1 there or not. It's optional. It'll default to 1. Any questions on the left-hand side? Now, what about over here on the right-hand side? So it's an array of chars. All right. So over here, is AR going to be constant? No, right? Because AR is in EAX. And if it's in EAX, it can't be constant. It's a register. So it's not constant. Well, 3 is, of course, constant. What about I? Is it going to be constant? No. And again, the reason I'm just asking you these questions is because if you ask yourself these questions, it's going to help you figure out where the things go, where to put them in. Right? So here, we're still going to have a move B now. We're still moving 55. Now, what's my expression over here going to be? So we know that the only constant part we have is 3. Constants have to go into what field? Displacement field. So it's going to be 3, or 3 times 1. Right? What do we want to put in the offset field? Do we want to put ECX, which is I, or do we want to put EAX, which is AR? How many of you vote for EAX? ECX. For this particular problem, it does not matter which order we do, because our scale is 1. But if our scale was not 1, what would we want to pick to put into the offset field? EAX, right? Where you want to start at. So %EAX. %ECX is the only other register field that we have. And then again, we can either put the 1 there or not. It doesn't matter. But again, if we were working with something besides characters, right? We'd wanted to have like, something like times 4. We want to multiply our index by 4. We want to move I integers or I floats. Or we want to move I words, I shorts, right? Here we want to move I characters or bytes. So 1 would go there, right? But you want to keep up the pattern. So hopefully you should be seeing that if we have our register, or we at the beginning of our array in a register, that register just goes here. This part over here is going to be like your variable offset, whatever it happens to be. And this is like how big each thing is. This expression over here is your constant offset. Right? How far do you want to move here? So now I'll give you a real challenge. Oops. Let's say we want AR plus J, or plus AR at I plus J plus, say, 5. And we're going to assume again that I is in ECX and J is in EBX. Discuss with the people next to you what you think the equivalent assembly expression is going to be to do this. And we'll go back to an array of integers. Or maybe we'll do an array of floats. Integers. Oh yeah. Okay, any thoughts about how we can translate this? Of course, you can use as many as you feel like. So sure, how do we can add I and j and put it into a new variable. How do we do that? Yeah, let's say we're going to use edx, right? It's available. So you want to move which register, EBX into EDX, okay, and then maybe you don't want to move, you want to add, right? ECX to EDX, right? So now EDX is equal to I plus j. Yeah. It's an array of integers now. Yeah. Like that. So you can't write a register times a constant like that, right? We can do this type of thing because everybody over here is a constant expression. But if you want to do multiplication with registers, you literally have to use the multiplication instruction, which we'll talk about a little bit later. But we could do scale of 4, and that'll work. So yeah, the trick with this one is just to add the I and the j together, right? You need to get it into one single register, that sum about where your variable offset is at. And it's just the same as the other problem, right? And if you really wanted to, you could have even done one more add instruction where you could have added 5 to the summation and then not had the 5 times 4 on the outside. Totally works. Now again, over here on the left-hand side, it's essentially going to be the exact same thing, except instead of AR, we're going to have EAX here. Any questions about doing this? All right, the trick is you just need multiple instructions, and quite often a single line of C is going to require multiple lines of assembly to produce. Okay, so now we got only 2 more left to do. Nope, don't do that. What about this? Discuss amongst yourselves how you would do AR at IJ equals 55. And again, we'll assume that AR is an array or is a 2D array of shorts. Good question, right? How did we allocate this array is going to really affect our answer, right? So let's assume that AR is a 2D, let's say a 5 by, say, 16 array of shorts declared statically like AR or short AR 5 16. So given this new information, how does this translate over? It's going to be what? It's going to be AR plus J. We got to write that, right? Huh? You don't use it, right? It's remember with statically allocated arrays, C, does it use row major or column major? So C, is it row or column major? It's row major, right? And with row major, the way that you compute the summation is it's each index times the size of all the dimensions that come after it, right? So with the row major, you never use the first index. And if it's column major, it's each index times the size of all the dimensions that come before it. So you never use the last dimension. So we got to do some multiplication now, right? Which is a new instruction. So let's pop that up over here. So let's say we want to translate, A times B, right? How do we do that? So one of the things about multiplication is that if you multiply 2 n-bit numbers together, the result can be up to 2 times n bits big. So if you multiply two 5-bit numbers together, right, you can end up with 10 bits as the final result. Or if you multiply two 6-bit numbers together, you can end up with 12 bits as the result, right? If you multiply two 32-bit numbers together, the result can be 64 bits big, right, which is bigger than what we can fit into a single register. So the multiplication instruction is a little bit weird, and it looks like this. It's just imul source, and the effect of this instruction is that edx colon eax is equal to source times eax. So the way to read this is the concatenation, right? So this just means the upper 32 bits of the product end up in edx, and the lower 32 bits end up in eax. So if you know your number is not going to actually be too big, you just ignore whatever's in eax. I mean, you ignore whatever's in edx because it's not going to have the result that you're looking for. So let's say that what we wanted to do over here is, let's say that A and B are going to be our results, and we or eax and ebx, and we want to do something like ECX is equal to EAX times EBX. Well, what you would do here, I guess, let's just set this up a little bit more. Let's say that EAX needs to be equal to 7 and EBX needs to be equal to 25. So the first thing that we have to do is put the 7 into EAX. So move L $7 into %EAX. What would happen if I didn't have this $sign here? What would the instruction do? Go to memory at address 7 and get the value that's there and put it into EAX. Then move L $25 to EBX. And then what we would do would just be imul %EBX. And our result's going to end up in EAX. And over here, we can then just do move L %EAX to %ECX. Copy the result over. But one of the things to really watch out for when using the instruction is that EDX will always be changed to something else. Will always be modified. So if you have something in it that you care about, move it somewhere else before you multiply. Hopefully that makes sense. And generally that's somewhere else generally means put it in memory because your other registers are probably full. Any questions here? Yeah.
Can you explain why there's only one EX after imul?
There's only one register after the imul instruction because that's how the instruction is formatted. It's just one of those ones a little bit different. And it always uses, and you're always going to multiply, whatever you say there by EAX. Any other questions? Yeah.
You're always going to multiply it by EAX because the next line says Mobilia.
I mean, this because this instruction right here, this is its effect. That's what the instruction does. So notice that EAX is always part of the product that's being computed, right? It's one of the multiplicans, whatever they're called. And that's just how this form of the instruction works. Anything else? So fantastic. We know how to multiply now. So what's this look like? So sure, we can do an imol. Imol by what? We're gonna get something to EAX first though, right? Move out, yeah, $16 into EAX. And then we can do our imol by ECX, right? That's gonna put into EC, this is gonna make EAX be equal to ECX, which is I times 16. Then we can do an addition, add L, percent EBX to percent EAX, and then we can do a move L, right? We want to start at our AR. That's the constant part. Again, our register is going to be EAX, and what should our scale be? Should our scale be? 2, because we have an array of shorts. Yeah, move L $55. Move W, yeah, correct. Any questions here? Like with the previous problem, like the I plus J, we have to like compute the total like value of the index that we want to use and then put it in there. Yeah.
So with the I will, why is it EAX being modified? How do I know that it's,
How do you know it's EAX?
oh, it's always EAX.
Because it's always EAX.
So it only uses EAX.
It also changes EDX too. We are going to put the upper 32 bits there, but if our number only fits into 32 bits,
So you only need
the lower half, yeah.
the lower half is EAX. So
Mhm.
EDX will change too, but we need some result before.
Yeah, if we had something that we cared about in EAX, I mean in EDX, we'd have to go move it somewhere else before we did the multiplication. So, if we pop back over here, let's do this side again. Nothing's really changing over here, except now, again, so now what do we end up doing? Is it going to be much different than last time? Everything we've done before? There's one minor complication. What is that? What's our small minor complication that we have over here on the right-hand side? What? No. What's an EAX right now? AR, but we need to do multiplication, so somewhere else, right? So move L percent EAX to where? Well, we can't put it into EDX because when we do the multiplication, what would happen to it? Right? We can't move EAX to EDX because it would be overwritten by the multiplication. Right? Remember, we have two other registers, ESI and EDI, that we can work with. Either one of them will be fine to use. So I'll just move it over into, say, ESI. And then pretty much everything else is going to be like the same down here after that one additional line of code, except that this guy now needs to be move L instead of AR on the outside. What are we going to put here? ESI, right? And we're done. Now, final one, and then we'll actually go and we'll do some problem Don't know why that keeps happening here. And let me get this up and running so that that's ready to start as soon as we finish. Okay, let's say again we're still doing AR at ij equals 55. It's still going to be a an array of shorts, but let's assume that AR is a dynamically allocated array of shorts. Dynamically allocated array of shorts, right? So you have something like, short star star AR, and then assume the space was dynamically allocated later on. How is this going to change things? How does this expression over here change? Discuss amongst yourselves. How does my expression over here change with the AR at ij? How could you rewrite that expression without using square brackets? Once you know the answer, you also get a free answer to one of your quiz problems too. What? Well, if you already finished your quiz, you should already know the answer. Good. Yeah, that'll work. But again, it's important to recognize that this expression means different things in different contexts, depending on how it was allocated. And you got to make sure that you translate it to the right assembly code to get the right effect. So we got a thought on how this should be rewritten. Given that we have an array of arrays instead of one big chunk. Right? Parentheses AR plus I dereferenced plus J dereferenced. That's what we have to do now. Okay. So when you're trying to translate this instruction, take it piece by piece. Do we know how to do this? Right? We've totally done this. Let's take that part right there. How can we get dereferenced AR plus I into some register? So move L, right? What do we want to move? How can I get AR plus I dereferenced into a register? Right? We just did that one multiple times, more or less. So which part of AR plus I is constant? It's just AR. So where does AR have to go? Into the displacement field, right? Keeping things consistent, our index, which is I, is going to be ECX. What's our scale going to be? But what's the type of, right? This is, right? When we dereference this, what's the type of this expression? What's the type of star AR plus I? What's this expression? The type of this expression. It's a short pointer, right? A short star, right? So we need to move I short pointers. How big is a pointer? 4, right? All pointers, regardless of what they point to, are 4 bytes big because they all store addresses, right? This is something you have to just be careful about here when you're doing things. You really have to know like what the types are and what's really going on to be able to write the correct assembly code. Where do you want to put this result at? Sure, you can put it in EAX, but let's put it in, say, like EDX because it's not in use, right? So now this guy right here, EDX, is equal to this little expression right here. So now how can I do the rest of the expression? Move L, parenthesis, what goes here? Right, this guy right here is EDX. So I need to do EDX plus J dereferenced. How do I do EDX plus J dereferenced? Or, yeah, we're moving $55 to so again, in this expression right now, this is EDX. Is EDX a constant? No, it's a register. So it can either go into the offset or the index field. Which field do you want to put it into? Offset, right? Because where we want to start at. Percent %EDX. The J is the percent %EBX. And then our scale is 2. And our instruction should be W because of shorts, right? Because at this point, when we dereference it, we're moving past an array of shorts, right? And each short is 2 bytes big. Any questions? And so what's going to change over here on the right-hand side? Well, it's essentially going to be the exact same thing, once again, except instead of having AR on the outside, we're going to have EAX on the inside. Any questions? Yeah. Why is the 2 here and versus a 4 up here? So the 2 on the bottom is because it's a dynamically allocated array of shorts. Yeah, so this expression right here, AR plus I, right, dereferenced, it is a pointer, but its type is short star, right? And so when you add some value to your short star pointer, right, you're saying move that many shorts past the address. And each short's 2 bytes big, so we're going to have to multiply by 2 to move that many shorts. Any other questions? Yeah.
The previous example, why did you use ESI? Like, I thought we could only use it general purpose.
You can use EAX through EDX and ESI and EDI. For the current or homework assignment, you can also get away with EBP, but not past the first homework assignment. And don't mess with ESP, except for when we start talking about how to mess with it. Because we will talk about how to mess with it, but like it involves a lot of stack operations like function calls, and so we'll talk about those pretty soon too, and how to make them happen. Are you guys ready to do an example? Okay. Because like the only thing we really haven't talked about how to translate are function calls. The only thing at this point in time. Classes, right, we talked about in when we were doing the information representation, and essentially like a class, right, or a struct, it is essentially an array, but the elements are of different sizes. But because you know what elements are going to be in there and what their types are, you know how far past the beginning of the struct you need to move to access the correct element. Take a look at the information representation slides about structs. If you still have questions, talk to me afterwards. Let's see. Okay, then we can do that. I just want to steal some stuff from. You know, that'd probably be much smarter. Let's just do it the smart way. So the first thing that we're going to do for solving this problem is we want to do matrix addition, but we want to do matrix addition with arrays that are declared as one big chunk, like above. Every single time you start an assembly project or assembly homework, the very first thing that you should do is write the C code. Because the C code is going to be a lot easier to write than the assembly code. Also, when you're debugging your C code, much easier to debug. So you can get out all of the logic errors and all the mistakes that you make there. And then if there are still mistakes in your assembly code, it's because you mistranslated some of the assembly code, not because you have logic errors there. So how do we write matrix addition? So we want to add A and B and put the result into C. Yeah, for loop. For int row is equal to 0, row is less than num rows plus plus row. Sure. Yeah, another for loop. For int call is equal to 0, call is less than num calls plus plus call. Right? All we have to translate these 3 lines of code. Shouldn't be too bad, right? No. I did, but it's okay because it's just a copy. Right? So over here, here's A. It's declared in memory. So just has some values here to work with. Here's B. It also has some values. The spaces are just help our visual distinction. We also have some EQUs just to help as constants to serve for those variables. So num rows is 3, num columns is 4. Word size, WS, is also 4. We've also made start global again so that the linker can find it so that we can compile the code. And then over here we have C, who is dot space num rows times num columns times word size, right? Because that's what it's how much space there is allocated as one flat chunk. You are free to make other things as we go along. So if you find out that we run out of space or we need something new, go ahead and say it. So now we have to translate this line of code. Before you start, you might want to pick some registers to play the roles of certain variables. So who do you want to be A? What register do you want to play the role of A? Or, right, there's two options. We can either use a register or we can use the label. Do you want to use a register or do you want to use the label? Register? Label. I think label slightly wins out. So let's say we use the label for A and we'll use a register for B to make everybody be happy, right? So what register do you want to play the role of B? EBX, sure. So B or EBX will be B. So how can we make EBX be B? B is equal to EBX is equal to B. Do you want this or do you want this? Dollar sign? No dollar sign. We actually do want the dollar sign. If we leave off the dollar sign, it's going to give us the first element. What's that memory at location B? So we'd actually get the value 100. Okay. Who do you want to, for C, do you want that to be in a register or do you want to use the label? Label? Register. Okay, I guess a lot of you guys want C to be in a register as well. Okay. What register do you want to be C? ECX? So sure, ECX will be C. And we more or less repeat this exact same line of code, but we changed the B's to C's. Okay. Who do you want to be row and who do you want to be call? Right, row, call. I will let you know there's no wrong answer here. You're just gonna pick someone. Well, I guess if you pick a register we're already using, that's wrong because you can't put two things in one register at the same time. So as long as you just pick some register besides the ones that we're working with, you're totally cool. So who do you want to be row? What register? EDX? Sure. EDX will be row. Who do you want to be column? You have ESI. So you have EAX, ESI, and EDI left to pick from. Sure, ESI will be call. So we're now doing this as our first line of code. So how can we make row be equal to 0? Move L $0 into. So row we said is going to be EDX. So EDX. This is why you need these commas here, right? Comments here, because we're going to forget what the heck is what really, really quickly, because I can't keep juggle all these variables in my head. So we're going to keep looking back here. So great, row is 0. How do I do the next part? This is what we covered on Tuesday. All right. You look at the slides. We go back to for loop. We have for start, but how many for loops are we going to have for this problem? 2, but can they have the same label? Right, we can have like row start or outer for or something start, right? So we can call it, a row start. So over here we have row start, or for row start. I don't know what do you want to call it. Okay, then what's the next thing that we do? Right, all of our comparisons have to be against what? 0. Is this comparison against 0? No, right? So row less than num rows, well, that's equivalent to row minus num rows less than 0. And its negation, because I always work with the negations for the for loops, is its row minus num rows greater than or equal to 0. Right? So what I have to do is I have to do this subtraction. How can I do row minus num rows? Comp L, right? Who goes first? Num rows or row? Num rows is going to go first, right? Remember, num rows, back here, it's an EQU. Num rows is just 3, so what do we have to put in front of it? $. It's a constant, right? Again, if we look back up here, num rows, it's an EQU. Num rows is just 3. So $3 to get the constant. And then on the right-hand side, we're going to have our row, which we said row is going to be EDX. Okay, that was the subtraction. And now what do we do next? Jump if greater than or equal to? Row n, right? And then down here, for row n. Okay, now we need to do plus plus row. Yeah, we just need to increment, so we can use increment. We want to increment EDX, which is a row. Yay, we did it! Right, for loop number 1, down. Next line of code. Oh yes, we do need the jump for start, my bad. Jump for row start. Now, here's our next line of code. Then we can translate, so what do we do? Right, well, what's the first thing that happens? Call, we said call is ESI. Is the font big enough for everyone to see? Does anybody need it bigger? You're good? Okay. Move L, $0 to, oops, $0. 2% ESI, right? As ESI is going to be call. This over here is the call equals 0 line. And this line over here was the row equals 0 line. Now, if we go inside here, our comparison has to be against 0, but it's not. So this guy, oh, we actually have our for call start. And then down here we'll have our for call end. Right, which this is going to be equal to call minus num rows, num calls, less than 0, and its negation is call minus num calls greater than or equal to 0. So we have to do the subtraction, which is we're going to do compile $num calls with again, call is ESI, right? That's the call minus num calls portion. And then JGE to for call end, yeah. And then at the bottom, we need to, well, increment column first, right? Inco call, which is again percent ESI. That's the plus plus call. And then yes, jump to for call start. Nice job. And now we just have one last little line of code to do. Right? I only made you translate 3 lines of code. Can't complain too hard. It's just 3 lines of code. Okay, if you rewrote this expression without square brackets, what's it going to look like? Star C. So how is this array allocated? Is it one big chunk, or is it an array of arrays? So up here, does this declare an array of arrays or one big chunk? It's an array of arrays. It's one big chunk. It's one big chunk. If you want to declare an array of arrays, you would see int star star. Right? If you're dynamically allocating an array of arrays, it's int star star. Also, if you look at our arrays, like here's A, does that look like an array of arrays or one big chunk? It's one big chunk. I just put the spaces there to help us visualize what's going on. So it's one big chunk, right? And we have to make sure that our translation here is one big chunk, not an array of arrays. Because if we do an array of arrays translation, it's going to break. Right? It won't work. So how is this, if all 3 of these arrays are array of arrays, translated? Right? We just did it. And remember, our arrays are num rows by num calls big. So this is plus row times num calls plus call is equal to this whole thing but A plus same thing B. Yay! Right? That's what we're looking at translating. Right? And so again, you guys are right. It looks like a lot. Now, what's the problem-solving strategy hopefully you guys have been employing so far to make big problems not so hard to deal with? Right? You break them down into smaller problems, right? We have how many smaller problems right here, at least at the high level? 3, right? The AR row call, the B row call, and the C row call. Right? So which one do you want to start with? Sure, let's start with A, right? Let's try doing this expression right here. And this is, again, hopefully what you guys are applying when you're doing your other, like, coding homework as well. And then you're breaking your problems down to smaller parts. Just a little bit smaller, 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 little bit smaller. A little bit of work at each level and eventually help you solve it instead of, here's the whole thing, right? I wrote a 500 long line main statement or something. I have gotten those as submissions. They're pretty intense to read. Seriously. It happens. Okay, so how do we translate this line of code? right? So we have to compute this value and we have to put it somewhere. Where do you want your somewhere to be? Again, there aren't really wrong answers. You can pick whatever you feel like. Where do you want to put this value at? We're currently not using EAX or EDI. Sure, so let's make sure that this thing ends up in EAX. Okay. What should I write? Right? We just did this more or less exact same problem. Right? So we can start by multiplying the row and num columns. So move L $, num calls to where? EAX. Okay, then wait. Why do we want to move num rows to EVX? I mean, like, this expression, does it involve num rows at all? Why do you want to put EDX into EAX? Well, I put number of columns into EAX, right? And we want to multiply. So yeah, we can do an imul. Imul by row. Row is in EDX. Right? So this is now EAX is equal to row times num calls. Then do what? Add L. Call is ESI to EAX. So now EAX is equal to row times num calls plus call. And then, but A is a constant, right? You kept it as a label. Right? But also we want to not only do the addition, but we also then want to go to memory at that location. Right? Since we're doing a memory access, what are we going to be using? The advanced indexing mode, right? The DOIS, the thing that we just spent all class talking about. So how do we do that? I mean, I did tell you. We spent all the class telling you. Right? Move L. A, it's the constant, it's a label, right? Comma. EAX, that's our variable offset. How big is each element? 4, which I have in word size, and we want to put that into EAX, right? So this is, EAX has now been set to this entire expression. Now before you go, remember, when we do this multiplication, asides affecting EAX, what other register did it affect? EDX, so what just happened to row? Oh, it's gone. We just overwrote that, right? So we have to go make sure to save that somewhere else, which we'll do that next week. See you then. The whole solution is already, though, up available on the Google Drive if you want to take a look.